All right, let's do some of this test here. First, we'll talk about radiation. All right, radiation or radioactivity is when atoms fall apart and they give off particles and energy as they change into other atoms. An alpha particle is big. It's got 2 protons that I made positive here and 2 neutrons. Therefore, it weighs 4. It has 2 protons, and it's just like the nucleus of a helium atom, and it has a positive 2 charge. Now, it goes through the air, but it can be stopped even by a piece of paper. Okay? We could do like a math problem with it. I could say we'd have 13 over 6C. That would be carbon 13. We could say that's going to alpha decay. Well, we would write 4 over 2 He plus plus, and then we would see what it would make. 13 minus 4 is 9. 6 minus 2 is 4. Number 4 on the periodic table is beryllium. And we could look up beryllium on the periodic table, and it actually does normally weigh 9. So if this happened, this would be a stable atom. Another type of particle is a beta particle, which is basically just an electron. So a beta particle is just an electron, which means it really doesn't weigh anything, has a charge of -1. A really famous beta decay is beta decay of carbon-14. When that happens, it gives off a beta particle. You can write a B here instead of an E if you want to. It gives off a beta particle. And then we say 6 minus -1, that's 7. 14 minus 0 is 14. The beta decay of carbon-14 makes nitrogen-14. Notice in beta decay, the mass doesn't change, and then the atomic number actually goes up. So that's beta decay. Why would beta decay occur? You have a nucleus like this, like 1, 2, 3, 4, 5, 6. That's carbon. 1, 2, 3, 4, 5, 6, 7, 8. This will be carbon-14. If a neutron broke apart and then became another proton, it would have to give off an electron to do that. And that's what beta decay is. You could stop this with some aluminum foil. Okay? But here's the catch. Anytime beta decay occurs, or alpha decay or beta decay occurs, you also have gamma radiation. And that's the dangerous stuff. Gamma is dangerous, okay? So alpha, beta, gamma. Another thing we can talk about when we talk about radioactive decay is half-life. Half-life means, let's say you have a bunch of unstable atoms. The time it takes for half of them to decay and turn into something else is the half-life. Well, then half of those would disappear, then half of those would disappear, then half of those would disappear, and then half of those would disappear. So that's how half-life works. If you had 100 grams of something and it underwent 3 half-lives, that would mean divided by 2, divided by 2, divided by 2. So you ended up with 50, 25, 12.5. You'd have 12.5 grams left after 3 half-lives. A half-life means divide it in half. So if this had a half-life of, say, 10,000 years, and you found 12.5 grams, and you knew there should have been 100 grams there originally, then you would know that it was 30,000 years old, because it had, to get from 100 to 12.5, it would have had to have halved itself 3 times. So you would know that that thing, if it had a 10,000 year half-life, you would know it was 30,000 years old. There's several different ways to ask this question, right? An isotope with a 4,000 year half-life would have how many grams remaining after 16,000 years if the original sample was 600 micrograms. Well, we would say, okay, it's got a 4,000 year half-life. 16,000 years went by. That means it underwent 4 half-lives, because 4 will go into 16 4 times. So if you started out with 600 micrograms, you could say divided by 2, 2, 2, 2. What does that equal? 300, 150, 75, 37.5. 37.5 grams would be remaining. Just hit divided by 2 4 times. So that's that part of the test. The other part of the test is about waves. Here's a wave right here. Here's another wave right here. This wave up top has a low frequency, but it has a high amplitude. This wave at the bottom would have a high frequency, but a low amplitude. If this was light, this might be red and this might be purple. Red waves are longer than purple waves, right? If we look at the color spectrum, red is the longest, violet's the shortest. Let's do a diagram of a wave. Crest, trough, amplitude, and wavelength. All right? Now, when waves move, they carry energy. Waves are moving energy. You need to know the formula. V equals lambda F. A 300 meter per second wave, that's how fast it's traveling, has a frequency of 60 hertz. What is the wavelength? Well, we would say V equals lambda F. The V is 300. The frequency is 60. So we're trying to solve for the wavelength. We move the 60. What's the opposite of times 60? Divide it by 60. 300 divided by 60, 5. 5 meters is the wavelength. You'll have problems like that on your test. Okay? Last thing I want to talk to you about the test. I'm sure there's some other things on here, but one of the last things is the electromagnetic spectrum goes from radio to micro to infrared to visible. These are the colors that you can see. To UV to X-ray to gamma. This is the electromagnetic spectrum. These are the longest waves. These are the shortest, highest frequency waves. Does that make sense? Infrared is a little too dark red for you to see. Ultraviolet's a little too bright purple for you to see. Microwaves are what cook your food, right? All of these go the same speed. They all go the speed of light. The behavior of waves, there's 3 big behaviors of waves. One is bouncing off. That's called reflection. Reflection. We saw multiple incidences of reflection today. All right? Another one is, let's say you have a drop of water and a light ray hits it. It's going to bend. That's called refraction. That's how a rainbow is made. So we've got reflection, refraction, and the last one, I'll draw a little diagram for us right here. The last one is called diffraction. If you have a rock in the ocean, this is from above, this is a picture from above, and the waves are coming at it, when the waves hit it, they'll just bend around it. And then they'll bend like this, and they'll just come back together, and they'll just keep going. That's called diffraction. All right? And the very last thing I would say is this. If you have a wave and another wave, if they're in phase with each other, they'll make the wave bigger. That's called constructive interference. If you have a wave and another wave comes by and it's the opposite or out of phase, that would make the wave smaller. That's destructive. All right.